Good day, everyone. I am Sarah Oni, standing on behalf of our team to present this paper, Mechanical Properties of Vulcanizates, produced from deproteinized natural rubber, compounded with monkey kola seed. This is the outline for this presentation. I'll be starting with the introduction, then characteristics of natural rubber, modification of natural rubber, justification for the study, aim of the study, materials and methods, result and discussion. Then we'll go on to the conclusion. Introduction. Natural rubber. The name rubber was actually given to it by Joseph Priestley in 1770. The chemical name for natural rubber is polycis 1,4-isoprene, but the word poly comes because it has numbers of repeating units. Among the natural rubber producing plants, we have dandelion, we have sunflower plants, then we also have fig tree. But we also realize that all these ones that have been mentioned, they can produce just little quantity of rubber that may not meet up with its commercial purpose. It's only the Brazilian rubber tree, Hevia brasiliensis, which is known for its commercial use. Then looking at this slide again, we can see two images at the lower part of the slide. We can see one is for tapping the latex from the trunk of Hevia brasiliensis, and the other one is the structure of our isoprene unit. Natural rubber has some unique properties which include flexibility, toughness, waterproof ability, and air impermeability. It doesn't allow air to penetrate through it. Although it has these wonderful, unique properties, it also has its own limitations, which includes being tough, being rigid, and this makes it difficult to process on large scale. So there may be a need to add fillers, things that can soften it so that it could be malleable and molded into shape. And it's also temperature dependent. What it means is that during hot temperature, it becomes very hot and sticky, and it becomes very elastic and easily draw it into any shape. But when it becomes cold, when the weather is cold or when the temperature drops, we realize that it becomes very hard and frozen. And because of this, there is a need to add fillers or things that can control its temperature dependency. Due to these limitations, Thomas Hancock of Great Britain invented a machine to facilitate rubber processing in 1820, and this was now followed by the discovery of vulcanization, in which many additives is added to rubber when heated, so that by the time it cools down, it could still be malleable and it could still be formed into shapes of the useful products that we need. And one of these additives is carbon black. But carbon black is very expensive, and that's what brings about the aim for this research. With this modification of rubber in mind, we also go into the chemical modification of rubber, which includes the proteinization, the polymerization, epoxidation, the acetylation, the hydrogenation. There are so many, but for this major research work, we are going to look at the proteinized rubber. The proteinized natural rubber was produced due to protein allergy. People were reacting to using just natural rubber. The protein that covers the rubber particles, the isoprene unit, was what people were reacting to, and because of that, there was a need to remove these proteins, and that gave birth to the proteinized natural rubber. This process can be carried out through centrifugation, enzymatic degradation, or irradiation. Mechanical properties of natural rubber. These are some of the properties that natural rubber exhibits when an external force is applied to it, and these properties can be measured in form of hardness, tensile strength at break, elongation at break, abrasion index, and modulus elasticity. Additives used in compounding. Carbon black is the most widely used additive in rubber industry, although there are other fillers like China clay and calcium carbonate. This carbon black is also derived from petrochemical sources, which makes it to be very expensive, although it has a very good reinforcing ability, and there is a need for us to look inward due to the cost of carbon black, since it is an imported material even in our country. We also realized that we could look into our agri products, carbonize them, and find out whether they can act as carbon black in its reinforcing ability, because with that we will also get fillers at lower prices and they are locally sourced. Hence, the use of kola lepidota seed was investigated as an alternative additive in this study. Monkey kola, which is also known as kola lepidota. Monkey kola is a common fruit in the southern part of Nigeria. It has some local names. For the Ibibios, it's known as Ndia. For the Fix, it's also known as Ndia. Then for the Igbos, it is known as Achicha. And we also learned that it could also be found in southern part of Cameroon too. This monkey kola is an edible wild relative of the West African kola nut, which includes kola laterita, kola lepidota, and kola rostrata. At the lower part of the slide, you can see two pictures, and this is showing the fruit. The pulpy part, the orange part, and this is the edible part. But for this research work, we'll make use of the seed. Justification for the study. Due to the limitations of natural rubber, by being temperature dependent, there's a need to overcome this limitation through the introduction of additives. But one of the best additives which we use is carbon black. And now we realize that carbon black is very expensive. And so it has moved us to look for an alternative source of additive that can be better or also have the same reinforcing ability like that of carbon black. In the process of deproteinization, we realize that the protein layer, which also is a stabilizer in the rubber latex, is removed, and its removal can affect the mechanical properties of this modified rubber. There may be a need for us to look for fillers to reinforce the deproteinized natural rubber. Hence the search for an agricultural alternative reinforcing filler, which could be obtained from our agricultural waste. And this waste can be converted into additives and used in natural rubber compounding. The aim of this study is to develop a low-cost alternative additive to carbon black, and we are looking at kola lepidota seed, which we also know that it's an agricultural waste. We want to carbonize this kola lepidota seed and also assess how it can be used in compounding, and to find out whether when mixed with the proteinized natural rubber could also give us the strength and the mechanical properties in which carbon black also gives to the proteinized natural rubber. That is what we are going to look at in this work. These are the material and methods, which include chemicals and reagents, and also the lab apparatus and instruments that were used for this work. This slide covers the preparation and characterization of the kola lepidota seed. The seed was purchased from Wat Market, and it was transported to the lab where it was cleaned, dried, ground, and sieved. And it was also characterized to check out the moisture content, ash content, volatile matter, pH, loss on ignition, iodine absorption, then the elemental analysis, which told us the element that was present in the seed. Then these seeds were now divided into two. When they were divided into two portions, the first portion was pyrolyzed in the furnace, while the second portion was not carbonized. After the preparation and carbonization of the seed, the carbonized kola lepidota seed powder and even the uncarbonized kola lepidota seed powder will now be compounded with the proteinized rubber, and the formulation goes as follows. We'll have the deproteinized rubber, sulfur, zinc oxide, stearic acid, MBTS in short, but in full is mercaptobenzothiazole sulfonamide, and we also have flectal H, which the chemical name is polymerized 1,2-dihydro 2,2,4-trimethylquinolone, with our fillers. And the filler loading will be in different percentages. We have 100, 75, 50, 25, and 0. And the vulcanizates formed will be passed through a compressed molding system. The vulcanizates were produced by mixing the different ratios of the components. The ratio of carbon black and filler kola lepidota seed powder were mixed in different ratios. In vulcanizate A, we had 100% carbon black plus 0% kola lepidota seed powder. In vulcanizate B, 75% carbon black plus 25% kola lepidota seed powder. In vulcanizate C, 50% carbon black plus 50% kola lepidota seed powder. In vulcanizate D, 25% carbon black plus 75% kola lepidota seed powder. In vulcanizate E, 0% carbon black plus 100% kola lepidota seed powder. With the compounding in different ratios, it was easy to assess the filler or which of the fillers had the better effect on the mechanical properties of the vulcanizate. After compounding, the vulcanizates were subjected to mechanical tests, but these are the results that we got from the characteristics of the natural rubber latex that we used for this study. And here are the DRC and the TSC, the ash content, the volatile matter, the moisture content, and the nitrogen content. These are some of the characteristics of the natural rubber latex that was examined. We got a result of 35.5% for our dry rubber content, which shows which can be defined as the coagulated rubber that could be got from the fresh latex that was tapped from the tree. Then the ash content too, we got an ash content of 11.26. This also shows the non-volatile mineral fraction that was present in the latex. Then also the hygroscopic nature of the rubber latex also depends on the moisture content, and we got that to be 5.07%. On this slide, the characteristics of carbon black was compared to that of kola lepidota seed, CLS, and carbonized kola lepidota seed, CCLS powder in the table on the slide. pH indicates the acidity or basic nature of a substance, and the pH readings for the fillers in this analysis at 28 degrees centigrade were found to be pH for the kola lepidota seed was 6.08 and 6.1 for the carbonized form of kola lepidota seed, which was also compared to that of carbon black, which falls on the neutral region of the pH meter, which is 7. And also the loss on ignition was also assessed. We looked at it knowing that with the rise of heating temperature there will be a particular loss. It was also noticed that the sample used, that the carbonized seed had a higher loss on ignition than their uncarbonized counterpart. Then Akilabi et al. Too had also stated that the loss of ignition is indicative of the carbon content of a sample used, and the more the carbon content, the better the compounding, due to the excellent network formation, and more bonds could be formed through cross-link. The images on this slide shows the scanning electron microscopy images for the carbonized kola lepidota seed, and associated with it is also the elemental analysis report that was obtained from EDX. So that's the spectrum of the EDX that is also attached. The spectrum shows the elements that are present in carbonized kola lepidota. It showed the presence of carbon, oxygen, magnesium. Carbon had the highest value with about 950 count, while also being closely followed by oxygen with 800 counts, then potassium and the others. The same image also obtained from the carbonized kola lepidota seed showed a cluster of group of agglomerated particles. However, when magnified, it was observed that these particles had a large deflective pore, which could also aid the formation of good vulcanizates. The pore seen in the same image of the carbonized kola lepidota is larger and more numerous than the one that we'll see in the next slide. On this slide, we are seeing the same images for kola lepidota seed, and we could see from this same images that the pores that are present here are not as numerous as the one that we had seen in the carbonized kola seed, and they are not as wide, or they are not as large as the one that we had seen previously. And looking at this too, we could see that the EDX spectrum still shows carbon, oxygen, sulfur, and potassium. This slide shows the Fourier transform infrared spectrum of the deproteinized natural rubber. The table is on the next page. This table shows the summary of the wave numbers obtained from FTIR of natural rubber and deproteinized natural rubber. There is CH bend, CH stretch, and OH. The values are close, but they are not identical. Here we come to the mechanical properties of the vulcanizate. The tensile strength of the polymer indicates the final strength of a material before its breaking point. The tensile strength was seen to be highest in the carbonized vulcanizate, as we will show you in the figures that are following the slide, when compared to their uncarbonized counterparts. This can be attributed to the carbon content that was increased during decarbonization. The hardness is also referred to the degree of resistance of a material from the penetration of an indenter. The higher values were obtained for harder materials than for softer ones. The more the quantity of the filler, the more rigid the vulcanizate. All fillers behave differently according to their different composition. This shows the tensile strength for the deproteinized rubber vulcanizates. Our vulcanizate ranges from A, B, C, D, E as they were compounded. The A is 100% carbon black. B is 75% carbon black, 25% filler. C is 50% carbon black, 50% filler. D is 25% carbon black and 75% filler, while our E is 100% filler, 0% carbon black. And we could also see the way it's going. The A acted better than others, then followed by the one that was 25% filler and 75% carbon black. The gray picture here, it shows that of uncarbonized kola lepidota seed, while the orange is the carbonized kola lepidota seed. And we can see the tensile strength here for the carbonized kola lepidota seed on B was much better than that was obtained for the uncarbonized version of it. So looking at it, yes, carbon black is still better, but we could also get something that is close to it by using our carbonized kola lepidota seed powder. The modulus elasticity for the deproteinized rubber vulcanizate is shown in the figure below. The trend of the tensile strength and that of modulus elasticity tends to resemble one another. For the A, that was carbon black, it's the highest. Then it's followed closely by B, which is 75% carbon black and 25% of the filler loading. The fillers here are kola lepidota seed, the uncarbonized version, and the carbonized kola lepidota seed. The kola lepidota seed is the one in gray, while the carbonized kola lepidota seed is the one in orange. And we could see that the one in orange, the carbonized kola lepidota seed, it's working and trying to be like carbon black, even though it is not as good as carbon black. But the result obtained from B can also be used. We could have a 75% loading of carbon black with a 25% loading of our carbonized kola lepidota seed. It should also aid to give us a good modulus elasticity. There is also a trend of decreased hardness from the 100% carbon black to 0% carbon black. The trend shows that carbon black is still the best, but it's followed closely by our carbonized kola lepidota, then our kola lepidota seed that was not carbonized. So the hardness could also be linked to carbonization or the presence of carbon or carbon filaments that helped in strengthening of these bonds. In conclusion, carbonized kola lepidota seed showed a trend close to carbon black in its reinforcing abilities, and this was also proved in how it worked in its mechanical properties. It could be combined with carbon black in simple ratio to obtain better results at low cost than importing reinforcing additives. The mechanical properties were also affected by the kind of filler, which you could see when we compared carbonized kola lepidota seed and uncarbonized. The carbonized kola lepidota seed acted in a better way than the uncarbonized one. It showed a better tensile strength, a better modulus elasticity, and hardness when compared to its uncarbonized form. The results from this vulcanizates showed that 25% substitution of carbon black with carbonized powders will not pose any deleterious effect.
These are my references, and thank you for watching.